Well, first of all, I want to thank the organizer for giving me the opportunity to talk about this work that we entitled Strain-stiffening Transition of Semi-Flexible Network. So I want to start acknowledging my main collaborator in this research project, that is Ida Lerner, and also our PhD student that have been working in this for a while already. Okay, so the main idea is quite simple. So you just imagine that you have some kind of biopolymer or some polymer network that is usually a semi-flexible polymer. In general, we're thinking about biopolymers, like the case of this fibrin network, as you can see in this picture, or also the problem of collagen, or actin network, or and so on. And so what the main idea of this experiment is just that you apply some shear stress in your system, and then you measure also the strain, how this is deformed, and you do this along all the strain curve, and then you can measure the shear modulus or any other elastic model. You could do the same with an expansion; it will give the same kind of result. So this is the idea, and the idea was to measure how it looked, this shear modulus. And this what was observed. This is in the first paper related to this field in 2005. What they observed is that for several of these kind of semi-flexible network, what they observed is that the shear modulus, it's remained constant or almost constant up to some critical or some transition strain, in which these start to increase very fast. Okay, so and this is not for all. You can see it in this case, for instance, for this network, it doesn't change a lot. Well, could be that something happened here, but for most of these RF systems, you see this kind of transition. And now the question if this is a kind of crossover, or actually it's have some kind of underlying critical behavior on this transition. Now, this is a very important mechanism, and you can think about, for instance, the collagen that you have in your skin, since you need to have something that is very elastic and very soft to deform in order that able you to, I don't know, to move or want something like that. But also you need that at some point, you can do your experiment, this stiffen very fast, and that you need because you need to keep thing, you need to hold thing on now in your body. So this is a very important mechanism for mainly for in biology. And so the question is, what is the underlying behavior of this transition? So the first experiment that showed that there might be some kind of critical behavior related to this transition was this done by Louise Jawert around 2013. And what she did is that she followed actually this node that correspond to this cross-link of this polymer. So she followed this point when they were straining the system, and she measured the non-affine displacement. That means when you deform your system and there are some affine deformations, so of course everything will follow some affine, but she measured how it deviates from this affine deformation. So this is what she observed. So you see that initially these two nodes did do some kind of rotation, and then it moved in a very affine way. And so what she observed is that precisely very close to the critical strain, okay, there was a peak, an increase in this non-affine and non-affine deformation, signaling that there might be some kind of critical behavior surrounding this transition. Okay, so what is the origin of this transition? So to understand this, let's come back to a very simple idea. Coming from the stability of reed networks. Okay, this is a very old field. So this is the main idea. Let's think that you just have some reed rod, okay, that are connected, like in this case. So now, in this case, if you have these 5 reed rod and you try to deform the system, you cannot deform. No, it's a reed structure. However, now if you remove this bond here or this rod here, now the system you can deform it, you can stretch it. But this is only possible until some critical strain. At some point, this just will become a line, and then you cannot continue stretching this anymore. So this is and this is what we understand now, this is the main mechanism related to this transition in this semi-flexible polymer. And I will show you a bit more about that in a minute. So just a few concepts. Floppy network then mean that we have some way that we can deform our system without changing the length between these two different nodes connected by a reed rod. And that can be written just in terms of this is the displacement of each of these nodes times the normal vector, that is, this is just the projection over this distance, so that means that the distance is not changing. And that can be written in terms of this is just some linear equation. I don't want to go into detail. This is just a matrix that we call S matrix. It will appear everywhere, but it's not really important. The only important thing that this contains information on the geometry of this network, okay? And this vector I will use this bracket notation, but it's just to refer to some large vector containing the deformation of this system, okay? It's not quantum at all. Okay, so now the Maxwell criteria will tell us that this network, our network, will be floppy if the number of constraints is smaller than the number of degrees of freedom for this system. And this can be rewritten in terms of the coordination, that is just the number of rods that are connected to each node. And then if the number of this rod connected to each node is smaller than 2 times the dimension, then the system is floppy, okay? And then we can say that usually the elasticity will be controlled to the distance to this critical point. Okay, so if the coordination is, in 2D, if the coordination becomes 4, then the entire network becomes rigid, and that's it. And if it is below, it will be floppy. So, of course, for our system, for the system that we are interested, they are actually, if we just measure the coordination, they are usually under-coordinated. So the basic structure of this network are floppy. So essentially, we are in some region. This is just the strain. This is the coordination. So we are in some region here. This is the coordination is around 3. And so now what we're doing is that we take one of these networks, and we start to strain it until we reach this critical point in terms of strain, and then the system will become rigid or will become stabilized. But you will, of course, the first question you will say, okay, but even if this coordination is smaller than the critical one in this region here, this system are not completely floppy. And of course not. These networks are stabilized because there are also some bending energies and some other energies related to the fact, for instance, that there is some energy because when you deform one of these nodes, of course, there's some energy related to that. However, that energy is much smaller than the energy that you need to stretch one of these links. Okay, so these networks are stabilized by this bending energy, but there is a separation in the scale between the energy scale and the stretching energy. Now, there have been a lot of different models recently to describe this kind of behavior. This I'm showing just a few of them. This is the Mikado model. I don't know exactly the name of this one, and there are several other, and all of them show rather similar behavior. And this is summarized in this work, I would say, that show how this shear modulus, in terms of the distance to this critical strain, show this scaling function, showing that there exists actually some kind of critical behavior. And there's 2 branches, of course. One is when you approach to the critical point from below. That means when you are in the floppy regime and you start to strain until you reach the critical point. That corresponds to this branch here. That is the one that I'm interested. And they observe that the critical behavior of the shear modulus, it's go more or less as delta gamma to the power minus 1.4. Okay, delta gamma is just the distance to the critical strain. These are experiments, and in the experiment in collagen network, and they observe some similar kind of exponent for this system. They observe that there is some difference in this exponent when they go from one model to another one, but usually it's around this minus 1.4, 1.5, 1.6, and so on. Okay, so what we wanted to do is precisely to understand this critical behavior and this exponent. So to do this, again, we introduce a new model. since there was already a lot. So we introduced a new model, but a model that allows us to have an infinite separation between the energy scale. That means essentially that we'll consider a model where it's essentially rigid rod embedded in some kind of soft elastic material. Okay, so now we won't have any stretching energy related to our rod. So this is our simple. We did different kind of model, but all of them are have the same idea. So we take some floppy network that you can deform of rigid rod, but these are exactly rigid rod. So in this floppy network, you have that you can deform it. This essentially means that you can deform this network. And then we try different kind of model. One of them, we add some energy, some bending model where you just add some energy related to the angle. So we define some initial angle, and whatever angle if the angle change, we have some kind of energy related to that. We also have some model where we attach each of these to some kind of confining harmonic potential. And also we try a model where we embed, we consider some elastic material. This is just elastic material. It could be also taken in the continuum limit. It doesn't really matter. That is characterized by this Hessian of the energy. And we embedded this network on top of the other one. And and this is how it looks. Well, this is a movie. It's not extremely impressive, but you can see how it's evolving. It's evolving and until it reaches the critical point that is that, and then you cannot continue stretching. Of course, the movie is rescaled, so it's to keep on the same size. But this is in this case, we are just expanding our system until we reach the critical point. Okay, so how we did this? Well, so we have to build or design the linear response theory of this kind of elastic material under constraint, and that can be done using, of course, the two main ingredient, that is the mechanical equilibrium and constant length of rigid rod. And what we end up is with some set of linear equation for the non-affine displacement and the strain derivative of the forces. And of course, this then we can solve numerically. Of course, we can also find an explicit expression for this term for the forces and the displacement in terms of the geometry. I won't go into the detail of this expression, it makes no sense. But important is that you can completely determine at some given time or strain the behavior of this system just in terms of the geometry of your network. Okay, but that's not the only good thing about this model, but also is that we can actually write some explicit expression for the elastic quantities or the different macroscopic quantities in your system. So this is just the elastic moduli, okay, that could be the shear modulus, the bulk modulus, depending if we are expanding or doing some shear deformation. And so what is now that we have this explicit expression, and now we can, under some simple argument or also just doing numerics, we can easily, okay, sorry, so we have this expression, this is the numerics, and what we observe is that for different models, this is the embedded model, this is the bending model. In each of these cases, this is different coordination. But for all of these cases, what we observe is that the shear modulus have some exponent that go like delta gamma minus 1.5. That is quite close to the one observed in experiment and in other numeric. Okay, but now we have the advantage that we can really go close to the critical point because these are really rigid rod. In the other case, at some point, the stretching starts to be important, and then you see some kind of crossover. Here we can go very, very close to the critical point. You can see here we have, in this model, like kind of a lot of order of magnitude showing this exponent. So what I was just telling you is that another interesting thing is that we can now see numerically or theoretically which of these terms are the most relevant one, and actually one can realize that what you can realize that actually the only term that is the term that is dominating here is just the last one here. Okay, so this is just the numeric. These are the different terms, and you can see that only this term here is the one that is really important, close to the critical point. And then this term here is not important the detail, but I will tell you that this is just a vector of order 1. Okay, this is just, you can imagine, actually in the case of an expansion, it's really just a big vector with just 1 on it. And so the whole critical behavior is contained in this f dot. So the physical meaning of this last term, What do you mean exactly with the physical meaning? Well, okay, this F dot is just is how the tension is changing with in your system. Yeah. So, I mean, it's expected that the shear mole. I mean, this is the shear mole is expected that it will depend on the tension in your rod and on the non-affine displacement. That is this. For that reason, I wrote it like this: is F the force, R dot, and also depend on the derivative of this tension. That can you imagine? You have your network, then you have some tension on it. So if the system, if this network become more and more, the tension increase in the system, that implies that make any kind of deformation become more harder. That is more or less how you can think about it. Okay. So, and why that is interesting? Because now we can have some model. I mean, I'm gonna show. I don't know how much time I still have. I still have a lot of time, I think. So actually, let me give you some very simple argument how I can explain this exponent. This is what we call the local argument. And so just imagine that you have this very simplified model. This are rigid rod, and this is just some spring to stabilize your system. Here you have some angle, and this is the distance between these two different nodes. So now, in a local model, I will say that the tension here, these tension are diverging. Yeah, so you can say that the tension here it's more or less the same as the tension in this other rigid rod, and these tension are diverging. While the energy related to this spring, it's not diverging. It's at the critical point it will remain finite. So actually, what you can say is that this just by the force balance, this 2 times this tension times this the sinus of this angle should be approximately constant close to the critical point. So that gives you that the tension should scale like 1 over theta. Okay, and on the other hand, you have that the distance to the critical point. The distance, the critical point will be when you have a straight line, so that will be just 2 times L. So the distance to the critical point you can easily calculate, and you will realize that you can say that delta gamma is proportional to theta squared. So then that gives you that the force scale like delta gamma to the power minus 0.5, and then F dot, it will go like minus 1.5. And since we know that the shear model is dominated by F dot, we know that the shear model should scale like this exponent here. Of course, you will say, okay, this is a very simple argument. Well, it's a simple argument, but it still explains more or less this exponent. One can do a bit better, but then what is interesting that we can show kind of the same, but in terms of a lower bound. We cannot show that it must be like this, but we can show that it must be bounded by this kind of divergency, in which we can show that the F square, the mean of the F square, it should be larger than some constant divided by delta theta square, where delta theta now is the distance, of course, to the angle at the critical point, because now the angle at the critical point it won't be 0; it can be something else. Okay. And then also using that if we are doing just think about some expansion, so you can imagine that then at the critical point the area or the volume of this expansion become maximum. So the distance to some other volume, it should go like delta theta square, and then you get that the elastic modulus should go usually. This should be actually something like more like something like this. It should go like delta gamma to power minus something larger than delta gamma to the power minus 1.5. Okay, so in our numerics for different kind of system, different kind of initial condition, we always observe the same exponent. So we could ask if this is the end of story and this bound is actually saturated and always will be like this. So to study it, to see if this was true, what we did, we used a slightly different scenario that now we thought in just a one-dimensional system, okay? One-dimensional in the sense of the reed rod network. This is the reed rod network embedded in some elastic network. And we give very different initial conditions. The first one is the one that is you see this is the angle. The initial condition is just plus alpha minus alpha plus alpha minus alpha. While this other, what we did is some Brownian motion or some random walk to define the angle. And what we observe is something very nice, that actually the exponent on the tension, it changed dramatically. In this case, you see F dot is go like delta gamma minus 1.5 as the previous case. But in this other case, F dot go like something close to minus 0.3, okay? So the question was trying to understand why that is happening. And we can solve a related and very similar model that is the one as showing here. So this is our 1D system. And now, to simplify a bit more our model, we replace the elastic field in the background by just some confining potential in each node. So essentially, when we evolve the system, it looks something like that. You can see it, to each of these nodes there's attached some spring. Okay, so this is like a mean field version of the previous model. Okay, and in this case, we can actually completely solve this system. And what we observe is that dynamics follow some kind of diffusion-like equation for the angles, and we can actually show that the way how the critical exponent on how this tension diverge, it actually depends on the initial condition of our system. Okay, so for different initial condition on the angles, we observe different critical exponent that saturate at for some initial condition. I don't want to go into detail. So okay, so that is pretty much what I want to tell you. Thank you very much for your attention.